Hello and welcome to a short video on the Schrödinger equation. In this video I want to provide some understanding of a problem that we looked at in tutorial 1. The problem is this. If we're given an eigenfunction, which is a function of position, and we're asked the question, what is the wave function, which is a function of position and time, then the relationship between these is the following. So let's just remind you that this is what we refer to as the wave function. And this is what we refer to as the eigenfunction. Now clearly they're intimately related. So for example, if I have a Hamiltonian operator, an energy operator, which acts on the wave function, or strictly speaking the eigenfunction, I have the following eigenvalue equation. So the Hamiltonian operator acting on the eigenfunction returns the eigenfunction. The word eigen refers to self or proper. And what multiplies this is a constant, which is a real number. And in fact, this is called the eigenvalue. Because the Hamiltonian operator is intimately connected to energy, this is in fact the energy eigenvalue. In general, there will be a set of eigenfunctions and a corresponding set of eigenvalues. Now here's the problem. If you're given the eigenfunction, and for the moment we'll suppress the index n, then how do you connect the wave function to this eigenfunction? And the answer is actually quite simple. You multiply the space part by something which is time dependent. Now this is only valid if the energy is a constant. In other words, this is a stationary state. And if it's a stationary state, then you'll know that if I take the square of the magnitude of the wave function and the square of the magnitude of this, then this right-hand term here is equal to 1 when I take the square of the magnitude, or indeed its magnitude. And so the probability density in this situation, where the energy is constant or fixed, or it's in an eigenstate of well-defined energy, is the probability density is stationary, it's time independent. So the full wave function, of course, depends on time, but the probability density is time independent. Now where does this come from? It comes from the following. What we do is we postulate that you can write in general a wave function as a product of two functions, one which depends solely on time, and the other one which depends one that depends entirely on position, and the second one which depends solely on time. And this technique will be used to solve the time-dependent Schrödinger equation, and this is known as the technique of separation of variables. And we'll find that this technique is used when you're solving problems in later part of this subunit. So let's show how this works. We're assuming that you can always factor in this way, and indeed that can in general be the case, but it's not the only way of solving these problems. So here's the time development or time dependent, or the full Schrödinger equation. And it looks like this. From lectures we see IH bar, partial derivative with respect to time, is equal to the Hamiltonian operator acting on t. In fact, the left-hand side of this is the energy operator acting on psi, and the right-hand side is the Hamiltonian operator acting on psi. So this is the total energy operator, and this is the Hamiltonian, and the Hamiltonian operator is none other than the kinetic energy operator plus the potential energy operator. So what I'm going to do is I'm going to assume that I can separate the variables by factoring it according to this prescription. So what I do is the following. I simply put in for capital psi, I substitute for this separable form, psi f. On the right-hand side, I have h psi f. Now you can see that f is the only function which depends on time. Psi does not depend on time. And so I can take out the psi and I get the following. Because this depends only on time, I'll turn the partial derivative into an ordinary derivative. And likewise, the Hamiltonian, as we're seeing from this eigenvalue equation here, the Hamiltonian acts on the spatial part, and it will give me the energy. So I can take out f here, and then I can act on psi. But since h acting on psi gives me the energy eigenvalue, then I can write this as E psi. Now this will only work if, as I said, the energy is fixed, it's constant, it's a stationary state. If it's making a transition between states, this factorization will not work. So what can I do now? Well, you can see that I've got on the right-hand side f psi, and on the left-hand side I've got psi and df dt. So let's divide through by both sides by psi f. When I do that, you can see that the psi's cancel here, and you can also see that the psi and the f cancel here, leading to the constant E. So what I have here is IH bar 1 on F times dF dt. And on the right-hand side, I have E. Now, I can also write this as F dot, but let's just leave this in its explicit form as dF dt. So if I rearrange this, you can see that I get dF on F. So I'm going to move the dt to the right-hand side. I'm also going to divide through by this, and you'll see why in a second. So if I divide through by IH bar, so I've divided through both sides by IH bar. That means IH bar is in the denominator here. The IH is cancelled because I've divided through. I'm also going to transpose this, and I get dF on F is equal to dt. And you can see that this is a simple differential equation whose solution is the following. If I was to integrate both sides, this means that I get log of f, because the integral of 1 on f is log of f. And then this is going to give me, well, just to remind you, I have E on IH bar, which I can also write as minus I on H bar E. Why? Because 1 on I is the same as 1 on I, and if I multiply top and bottom by I haven't done anything, but I times I is minus 1, and so this is the same as minus I. So this then gives me minus I on H bar E t plus some integration constant. Now, the final step is simply to exponentiate this. When I do so, I'll get f of t is equal to e to the minus I e t on H bar. You can show that the constant e to the c, in fact, is just equal to 1, and I invite you to impose suitable initial conditions to demonstrate that. And so now you can see that this general time-dependent term here has got this form, e to the minus I e t on H bar, And this works providing E is constant, which implies that we have a stationary state. So in general, if you're given a eigenfunction and you're asked to compute the wave function, you simply take the given eigenfunction and you multiply by this exponential form, where E would be the energy that relates to the specific problem you're dealing with. So for example, if you're dealing with a particle in a one-dimensional box, then we know that from first year that the eigenfunctions are given by this. And the eigenvalues are given by this. Where L is the size of the box. So if I ask the question, what's the wave function for a particle in a box in the ground state, the lowest state, then it's going to be the eigenfunction for that particle in the lowest state multiplied by e to the minus I E1t on h bar. But psi 1 of x, I just put n equals to 1. And so if I write this out explicitly, it's 2 on L, which is a normalization constant. It's n is equal to 1 pi x on L. And then I put in the value for the exponential using exp rather than e because it makes it a little tidier to write. It's minus I on h bar. And then E1 is 1 squared pi squared h bar squared on 2ml squared multiplied by t. And that would be the full wave function associated with this eigenfunction. Finally, you can show that if I was to take the magnitude squared of this, you can see that the magnitude squared of this is simply the square of this function here. But you can see that when I take the magnitude of this is essentially e to the minus I times some angle, where this angle is all of these constants here. When I take the magnitude of that, that's just 1. That's a circle of radius 1, which just shows you that for an eigenstate, when the system is in an eigenstate of definite energy, in this case E1, then the probability density is independent of time. It's given simply by the square of the magnitude of the eigenfunction. So I think that should give you enough information to proceed with many of the questions in tutorial 1, and indeed many of the problems from the problem sets from the 2061 quantum mechanics, previous quantum mechanics problem sets.